Welcome everybody to today's Badger Dairy Insight webinar. Today we are going to be talking about tools for your dairy toolkit to keep animals healthy. I'm Melissa Seefeld. I'm the dairy and livestock educator here in Eau Claire County and will be your moderator today. And we have some other educators on that will be assisting with questions and helping make sure that we get all of your questions answered today. We've got Ryan Sterry on from St. Croix County. We've got Jackie McCarville on, who's based out of, I'm going to get this wrong, Greene County, and Heather Schlesser out of Marathon County. So all here to help you make sure we get your questions answered. So without further ado, I'd like to introduce our first speaker, who is Dr. Neslihan Akdeniz. And she is an assistant professor and extension specialist in the Biological Systems Engineering Department at the University of Wisconsin-Madison. Prior to this, she was a clinical assistant professor at the University of Illinois at Urbana-Champaign. And her fields of interest include livestock and poultry environments, air quality, energy efficient ventilation design, greenhouse gases and VOC emissions, and nutrient utilization. If you have questions, feel free to drop those into the chat for us, and we will answer those at the end of each presentation that we have today. And we have a couple more speakers after Nestle. So with that, the floor is yours, Nestle.
Yeah, thank you very much, Lisa. Yeah, thank you for the introduction. So let me see. All right, so this is my first slide. So good afternoon, everyone. I am Neslihan Akdeniz. So today's topic is dairy ventilation. So it's a big topic. So I will cover some basics, some options, and then I will cover some aspects of energy consumption and what is the relationship between ventilation design and greenhouse gas emissions. Is there a relationship between cost and GHG emissions? Okay, so let's start with some basics. So what are the parts of a fan? So I just want to cover some of the basics first before we move into calculations. So when we think about a fan, it can be a ventilation fan or it can be a circulation fan. One is the propeller, which is directly related to airflow efficiency. Then we have the drive system. So it can be a motor with belts. So when there's the belt, we can see a schematic here, it has higher efficiency. But then there's a belt there, so that belt requires some maintenance. So those fans require higher maintenance. And then it can be a direct drive. Some of the fans are direct drive, actually most of them are, but we have a lower efficiency since there is no belt system there. But since there is no belt, it requires less maintenance. Housing of the fan, it can be a metal or a fiberglass or something like durable plastic, since there is humidity inside livestock buildings. So, and then there are some gases, and some of these gases are very corrosive. So the housing of the fan should be something durable. Guards are important for safety. Most of the ventilation fans I have seen so far, they all had guards, so important. And shutters are also very important. So if we don't have a backflow prevention system on a cold day like this, we might be blowing cold air inside the barns, even if the fan is not on. Okay, so let's look at an example. Okay, so here we are seeing an example. So this is an exhaust fan. It is specifically designed for a livestock building. So this is a 36-inch, not super big, not very small. It's the fiberglass variable speed exhaust fan. And the manufacturer says this is designed for a tunnel ventilated livestock building. And one of the things that they promote is it is very corrosion resistant. So all the screws, all the parts are made of stainless steel. So here's another example. We see this is a tunnel ventilated building, and these fans are connected to the short end of the building. So each fan has a different ventilation rate. So what is the actual ventilation rate? So most of the livestock buildings, the ventilation system, mechanically ventilated buildings, they work under negative pressure. So these fans are drawing air through the barn to the outside. So, but what is the ventilation rate? So all fans are different, and it really depends on the brand and company name and the model number. But if it is a certified fan, there is a certified fan performance. And there are two labs in the United States that they do this certification. One of them is Air Movement and Control Association. They are located in Chicago area, so they are very close to O'Hare Airport. And if you're familiar with AMCA, they have a lot of standards. They have a lot of guidelines. So it is one of the labs. It's the nonprofit organization. The other one is BESS Lab. So it is Bioenvironmental and Structural System Laboratory. So it is located in university, actually in AB department at the University of Illinois. So it is where I was located, and I had a chance to observe how they test those fans, and I will show you some pictures. Okay, so this is how the lab looks like. So they updated the lab. So now they are able to measure bigger size fans. So this is this red and white structure. It is their lab. It is how it looks like. So if you go ahead and Google BESS Lab, so probably the first link that will come up is their link. So you will be able to reach out their website. So you will see they have tabs for ventilation fans, and they have tabs for circulating fans. So once you click them, you will see a window like this. So you're able to choose current performance tests, or you can reach out to their archive. So they have a very big archive. You can get the results for maybe more than 20 years. So I have seen a result when I was preparing this presentation, like from 2000. So you can look at their archive or current performance tests, and then you can choose the power supply. So this is an international lab. They receive fans from all around the world. They receive fans from China, from Brazil, from Europe. So in the United States, it's mostly 60 hertz. But from other countries, then the power supply might be different, and they're able to handle that one too. So you can choose the manufacturer, or you can say, I want to see all manufacturers. What are my options? You can choose the fan diameter, airflow, and you can choose the efficiency ratio. There is something called ventilation efficiency ratio, and it is CFM per watt. So CFM is cubic feet per minute. So the volume of air we are drawing from a barn in 1 minute versus how much energy we are spending to do that job. So it is called efficiency ratio. So if you don't want to choose anything, if you want to see all your options, you can see all manufacturers and submit the form. So something like this will come up. So there will be a long list of fans, and you will be able to choose the model number and the brand name you want, and then you will be able to reach out this information table. So on this table, we see this is the 55-inch fan, and the housing material is plastic. So they enter some basic information here. They enter the test date and some other basic information that you may want to look at. But more important than that, they will provide you this table. So here we are seeing the static pressure versus airflow rate and the ventilation efficiency, which is CFM per watt. So static pressure is kind of difficult to explain, static pressure, but we can think about it like it is the resistance to flow. So for instance, if you picture a tunnel ventilated building, so there are stalls, there are cows, So they all show some resistance to flow. So there might be some structures inside the barn. For a cross-ventilated barn, there might be baffles, so they increase the static pressure. Your air inlet size, if it is not designed correctly, if the air inlet size is too small, then it will be difficult to pull air outside of that barn, through that barn. Then the static pressure will increase. So they test the fans at different static pressure values. So to be able to do that one thing they have is they have a very big fan that is working against the fan they are trying to test. So when this is pulling air this side, this is pulling air this side. So it is increasing the static pressure so that they can reach out all these numbers. Another thing they do is they have this system and then they can plug these holes. So once they plug, it depends how many holes they plug, it increases their static pressure. So they are able to provide you this table. So static pressure is never zero, but we want it to be a small number. So if it is 0.05, it is a good design. So if it is 0.15, I think 0.15 is acceptable. I have seen some buildings with a static pressure 0.2. It is maybe still acceptable, but we don't want to see a number bigger than 0.2 probably. So let's look at an example. Let's look at this static pressure at 0.15. Our airflow rate is 25,000. So let's look at an example. So this is the data from Midwest Plant Service 34. So they report the airflow rate requirements for mature cow. So in cold weather, they usually say 50. In mild weather, like warmer weather, it's 170 CFM per cow. And for hot weather, so this number used to be something like 460, close to 500 CFM per cow. But nowadays, they're recommending 1,000, 1,500 levels. So it really depends. So it depends on the volume of the barn. So maybe the stall size is constant in each barn. So it depends on how many animals you put. So maybe the width and the length of the barn, they don't change, but the height of the barn varies a lot. So some barns, they have a big roof structure. So the volume is bigger. So it is harder to pull air through. So if it doesn't have that, if it has a false ceiling, if it is flat, a lower height, it is easier to pull air through. So this 1,000 CFM per cow in hot weather, it is an assumption to achieve 40, 60 air exchanges per hour. So let's use 1,000 for our example. So for cold weather, 50 CFM per cow, let's assume 500 cows inside. So if we have only one fan, we will be able to achieve that cold weather ventilation. So mild weather, so it is 170, we still have 500 cows. So we will need 85,000 CFM. So we had one fan. If we turn on 3 more fans, then we are good to go. So hot weather examples, so if we assume it is 1,000 CFM per cow, so we will need 20 fans during hot weather. So if we had 4, we need to turn on 16. Probably we need to do one more calculation here. There needs to be a transition from 4 to 16. We will not suddenly turn on 16 fans probably. But in general, if we have 20 fans, that will do the job. So let's look at this data. So if we have 20 fans, so assume that you have a tunnel ventilated barn and you put 20 fans on the short end of the wall, and that it may work, right? There is a possibility if all of them are running and if your calculations are correct, it may do the job. But during cold weather, right, we will turn off 19 of them and only 1 will be working. So the question there is, which one will be working? So if you choose the one in the center, it will just pull all air from the feed alley and your cows on the side, they will not get any fresh air. So if you pull air from the right side, then left side will be suffering. If you pull air left side, then right side will not be happy. So it is not possible to achieve that ventilation rate only with one fan. I mean, we can achieve the ventilation rate, but the air will not be distributed evenly. So I think one option is to have variable speed fans. So a fan that we can say, okay, it is cold now, you only work 60%. And then when it gets warmer, then you can work 90%. So we don't want fans to work 100%, then it reduces their efficiency, but it's good to be able to have some control over the fan speed. All right, so here we are looking at a naturally ventilated barn. So this is a very good example. It's very bright and breezy. So we see the curtain side walls. We see the rich openings on the ceiling. And most importantly, we see the circulation fans. So the difference between a ventilation fan and a circulation fan, ventilation fan brings in the fresh air, outside air inside, and circulation fan makes sure that air is distributed evenly and each cow has a chance to get some fresh air. Okay, so here's an example of cross-ventilated barn. So this is a very good example. So probably we should all go and visit this barn. So the air quality inside this barn was exceptional. I could stay there all day long and I wouldn't mind at all. So this is it's a little bit difficult to picture the cross ventilation since we need to see the whole surface, but I will show you a schematic. So this is the air inlet and they have the baffles here. So we see one of them. And then this is the other side. So these fans are heading to north. So this is where they are pulling the air outside. Again, it is negative pressure, mechanically ventilated building. So, okay, let's look at a schematic of it, same barn. So what I do for my research is I visit livestock buildings and then I draw their schematics and then I calculate. So I have a lot of what if conditions. So I test all those conditions using modeling. So what if all cows are standing? What if all cows are sitting? What if the inlet is heading to north? What if the inlet is heading to south? So we can test all those conditions. So there is no way that we can go ahead and test whatever comes to our minds in the field. It is too expensive, right? But once we test them using our simulations, then we can go ahead and, if there is anything promising, right, we can go ahead and test them in the field. Okay, so we see the fence here, and this is our inlet, and air flows parallel to the animals. So it is cross-ventilated building. All right, so here we see the temperature distribution. So again, this is our inlet, and this is our outlet. So it is the assumption here is outside temperature that day is 28 degrees C. So it is the average summer temperature in Wisconsin. So we see some red spots here, but they are basically cow body temperature. So the outlet temperature is like this blue or light blue, light green. So it doesn't increase a lot. So we are in the range of 28 degrees C to 29 degrees C. The difference is less than 2 degrees C. So it does work. It is a good example. Okay, so I wanted to show you this one. So this is the cross-sectional view. So these are my baffles. So I have 4 of them, 1, 2, 3, 4. So these baffles, they increase the static pressure inside the barn, but at the same time, they help with the velocity a lot. So in my opinion, they are a very good idea. So let's look at this example. So air comes and it hits the baffle. So this light blue, if you check here, it's a little bit faster. So it gets faster, velocity increases. It comes and it hits, and then velocity increases again. So we are able to achieve that one. that mixing effect, or like making it a little bit go faster. And if you stand under a baffle, you can feel it actually. You don't need to have any modeling or simulation. And here we see the temperature distribution. Again, this is our inlet and this is our outlet, and we can see the cross-sectional temperature distribution. All right, so this is another good example. This is tunnel hybrid ventilation. So this is a relatively old building, so it is naturally ventilated. But then the owner of the barn, they added some ventilation fans at the end of the barn, and they converted it to a tunnel hybrid ventilation. So this is a good example, since in winter, they can turn off all their fans. Tunnel ventilation, it doesn't work very well in winter, but they can use their natural ventilation. We can see the curtains here and the ridge openings here. It can be a naturally ventilated barn in winter during cold weather like today, or we can look at the ventilation fans. They can turn on their ventilation fans in summer when it is very hot outside, and then it can be a tunnel ventilated barn. So usually during tunnel ventilation, we put these fans on the short wall. So they usually don't fit. So they need to put some of the fans on the long wall too. So all tunnel ventilated buildings I have seen so far, they work like this. All right, so again, a schematic of that one. So this is the inlet and these are the outlet. These are the ventilation fans. We have more ventilation fans here, which we cannot see. But here we see the roof structure and we see the ridge openings that allows natural ventilation in winter, and we can see the curtain side walls. All right, so I covered some basics, and I think the question is like, okay, what are you trying to communicate today, right? So we understand these are the basics. So let's look at some data. Let's look at some calculations here. So there is a lot of data available, but I chose to use this data from Minnesota. So this shows the energy use on a dairy farm. And according to this resource, ventilation accounts for about 19% of the energy use on a dairy farm. Okay, and then this data also varies a lot. So it can be any number between 800 to 1300 kilowatt hour per cow per year. So how much energy are we using every year on a dairy farm? So let's assume it is 1200. Okay, an assumption. And then I chose 700 dairy cows. 700 is slightly under 1000 animal unit, but it is kind of at that range. So it is a large animal feeding operation. So let's multiply these numbers, and then we assume it is 19%. This is the ventilation rate. So we consume 160,000 kilowatt hour per year. So if we assume the electricity cost is 10.9 cents per kilowatt hour, then we spend $17,000 per year. So it's about 25 per year. Okay, so what does this number tell us? Is it a big number? Is it a small number? What does it say? So I'm not an agricultural economist. Probably I am the last person who can talk about this, but I want to share with you this information. So I collected this information from ERS, USDA. So they last updated last year at the end of last year. But this is the data they are showing for 2021. Probably 22 information is coming soon. So they report the US average. US average means the average of 20 states, milk producing states. And then they report for every state. So I'm showing you Wisconsin data. So when we look at the gross value of production, so 19.16 for US average, all units are in dollar per 100 weight. So Wisconsin is in good shape. So we are a little bit higher than the average. When we look at the operating costs, So this is a long list, right? So at the top of the list, there's feed costs. So feed cost is the major expense on a dairy farm. But then, since today we are talking about energy use, electricity consumption, I included that one. So feed costs, Wisconsin feed cost is lower than the US average. Again, it is good. When we look at the fuel and electricity, it is a little bit higher than the US average. So there might be different reasons for that one, but I can kind of see there might be some room for improvement here. And then we have the labor cost and all cost, and then we can look at the net value. Okay, so this is the net value in 2021. So it is the value of production minus all costs listed. Okay, it is a negative value. So when we look at the 2020 data, it was minus 1.59 and minus 0.73. So in 2021, it got worse, basically due to increased fertilizer prices affected the feed prices. Then there was labor shortage due to maybe pandemic, and all they end up. So, and then it did affect the net value of production. So I know it is not that simple, right? But I kind of feel like for us, there is some room for improvement, okay? So what can we do, like related to fan design, ventilation design, fan selection? So one of the things we can look at is we can choose our fans correctly, okay? So two fans may look like exactly the same. So I am showing you two examples here, the fan A and fan B. They are both 36-inch fiberglass fans, but different models, different brand names, okay? So if you look at the fan efficiency at 0.05, this one is 16 CFM per watt. This one is 18.9 CFM per watt, okay? So how much does it matter? Let's say it's 16 CFM per watt, and then we multiply it by the cost of the electricity, and then we assume 700 cows in our building. So we are spending 480 cents per hour, okay? And then let's assume Wisconsin summer hours. So this is the number of days or number of hours. Temperature is about 20 degrees C. So every summer, if we use fan A, we are spending $8,000 per summer, okay? So if we do the same calculation with fan B, this time we are spending $6,800 per summer. And there's $1,200 difference between them. And if we use these fans for 10 years, so the difference is $12,000. So if we are not gonna buy fan B, and if we are gonna buy fan A, then there has to be a good reason, right? Either the initial cost of fan A should be lower, or should be more durable, or they should have a better service. Otherwise, every summer we are losing some money. So I didn't include mild weather or cold weather ventilation. We can include those two, then the difference will be bigger. Okay, so let's look at another example here. This is fancy. So fancy, I purposely put an extreme example to be able to see the difference. So it has a smaller fan size. So it is an 18-inch fan. Okay, once the fan size goes down, then the efficiency goes down. So ideally, we prefer big fans that are working slowly, but then the air distribution inside the barn is difficult to do. So we need to find the optimum way of doing it. So if we think about fan C and fan C efficiency, then the difference becomes $8,000 every summer we are losing. So we need to take all these into consideration. So not just the initial cost of the fan, but we need to be able to check this fan efficiency, and then we need to think all of these. So, all right, another thing, once we select our fan maintenance. Okay, so there is a lot of information online available. They say if you don't maintain fans, they can reduce efficiency by 20 to 25%, up to 40%. So this means that there are two options. One, electric bills will stay the same, right, if the fan efficiency goes down, but less air will move through the barn. So instead of having 40 to 60 air exchanges in hot weather, we will have 24 to 36 air exchanges. Is it possible? So do you think you will not notice if less air is moving through the barn? So I'm pretty sure farmers will notice because their animals will tell them, right? Then they will take a measure. So there are a couple of options. One, they will say, okay, the system I have is not sufficient enough, so they will add more ventilation fans. Or maybe they will take another measure. Maybe they will have a sprinkle system, or maybe they will have an evaporative cooling system, or they will add more circulation fans. So the assumption here is energy consumption can increase up to 40%. Okay. So how does it affect the price? So the price will go up, right? So the amount of electricity we'll consume will go up. So if instead of spending 73,000 kilowatt per hour, if the fan is working only 60% efficiency, it went down 40%, then it will be 122 kilowatt hour we will spend every summer. Okay, we understand the energy consumption will go up 40%, but what are the other considerations? Another thing that will go up is the greenhouse gas emissions. Okay, so now I am explaining the relationship between the greenhouse gas emissions and the ventilation rate. So there is this tool, it is called Comet Farm Tool. Okay, we can go ahead and enter the amount of electricity we consume just for our ventilation fans based on our calculations. It will not allow you to enter any number unless you enter your zip code. So you enter your zip code and then we enter our electricity consumption, okay, kilowatt hour, and it will calculate you. So this is the unit is pounds, total CO2 equivalent GHG emissions in pounds, okay? So if fans are well maintained and they are working properly, this is the greenhouse gas emissions. If the fans are not maintained properly, then greenhouse gas emissions will increase. Okay, so in this example, they will go up 66%. We will see a 66% increase in GHG emissions. So we see this 198,000 and 119,000. So, you know, well maintained, not maintained. So, okay, so why do we care about GHG emissions? Why is it important? So we care about it so that it is nowadays USDA provides a lot of funding, right? The climate smart practices are gaining attention. So in the past, when we think about carbon credits, the only thing that came to our mind was anaerobic digesters. Nowadays, we are talking about cover crops, we are talking about rotationally grazed pastures. They are also climate smart practices, right? So I'm hoping we will reach to a day that a good ventilation design will be also a climate smart practice, and dairy producers will be able to gain credits for maintaining a good ventilation system. So fan maintenance, probably everyone knows this one much better than I do. It is a dusty environment, and I do accept it is not possible to keep these fans completely clean. So, but please remember, even a thin layer of dust, it decreases air movement. So we need to do our best as much as possible, disconnect power supply and clean these fans and inspect for cracks. If there are belts, maintain belts and look for the loose bolts and screws. So we can measure the airflow rate of a fan. We can just use a small tool and test if it is working or not. All right, so these are my final thoughts. I think I am almost on time. So what are we paying attention? So we need to calculate the necessary ventilation rates based on the number of animals we have, and then have correct air inlets. If the air inlet is not designed correctly, static pressure will go up, ventilation efficiency will go down. And then we need to look at if it is a certified fan. There is no reason not to buy a certified fan. We need to look at that certification, choose the best option for us. We can consider different ventilation options. What that dairy producer did, converted a naturally ventilated barn to a hybrid, added some ventilation fans. It became a tunnel ventilated barn. It's a very smart idea. And then maintain fans when possible. I understand we cannot keep them completely clean. And remember, having a good ventilation design is a climate smart practice. All right, so it is my time. With that, I want to open it up to questions.
Yes.
So I can stop.
Come through the chat.
All right.
Yeah, so we did have a question come through about why do you want the static pressure in a building below that 0.2? Like what happens if it's higher? Is it making the ventilation system not work as well? Does it, make it work harder and so it doesn't last as long? What's going on there?
So static pressure is the resistance to flow. So if static pressure is high, let's say we have a very small air inlet, it is not designed correctly, then static pressure will be above 0.2, right? Then it's so difficult to pull air. So fan will be working very hard, but it will not be able to draw the air through the barn. So the efficiency will go down. So we will spend more energy to be able to draw the same amount of air through the barn.
Thank you. We had another question. We commonly run into scenarios where we have farms that are looking to retrofit or improve older facilities. In addition to the fan needs that you've discussed today, do you have any other like resources, go-to things for determining that inlet sizing to make sure that we have that right?
So one thing that one of the projects I'm working on right now, they are converting an old tie stall barn, which they are not using anymore. It's a very small structure for housing cows, so calf barn. So then we are kind of trying to come up with a tube ventilation design which can be used during cold weather, since for lactating cows, maybe winter ventilation is not that critical. Summer ventilation is important for them, but for smaller animals, winter cold weather is important. We want to provide them fresh air, but we don't want to have the draft on them. So it might be an example, and I may be able to come up with some resources related to that one.
Okay. We have one other question that came through, but I do want to remind everyone we do have some poll questions up. So if you could take a couple of seconds and fill that out for us, that would be much appreciated. And Nestle, our last question was, we used to have a specialist in biological systems engineering that had a spreadsheet that helped determine that fan size. Is there something like that that exists? I think there might be something that the vet school has. Can you point to any resources like that are out there?
Yes, so fence size, it really depends. So I showed a couple of examples and I said it depends on the height of the barn. So if they can reach out to me, I can be able to provide them some guidelines. But we don't have a formula that fits to any kind of condition. So if we have circulation fence, then the ventilation rate requirements will go down. So if it is a high ceiling, then it will go down. If it is a false ceiling, then it will go low. So it really depends on those conditions. Yep.
Okay, so it sounds like if we have questions on that, definitely reach out.
Yeah.
Okay.
Yep. Please reach out. Yep.